Now we are going to hear from Adam Markiewicz from Akademeia High School, and he will tell you about what happens when teachers have their own toys that they can use for all kinds of purposes, 3D printing for education. Thank you.
Together with Darek, we teach physics in Akademeia High School, and today I would like to talk to you a bit about our endeavors with 3D printing and how we have managed to use 3D printing in our physics classroom this year. And first of all, I would like to say that we had a 3D printer before, like it was standing for, I believe, 4 years in our lab's prep room, and it wasn't used much. And what allowed that change to happen? So our alumnus, Henrik, decided to take a gap year before going to university. He finished school last year, and he was looking for some interesting opportunities something to do during this gap year, and we knew that the guy is great with practical physics with building stuff and very experienced in 3D printing, so we offered him an internship as our lab's technician. And he happily accepted our offer, and it was really match made in heaven because he had a lot of experience, and it was possible for us finally to come to him, sell him an idea for an experiment or a demonstration, and he would translate our idea into a 3D model that can be printed, and he would print it for us and prepare everything, something that we simply didn't have time for before. So, a few examples of the things that we have achieved. And what we have learned, and what worked, what were the challenges. So first of all, loudspeaker. So here you have it, a very simple design, and it's actually something that I have found in one of all the GCSE exams. We teach British curricula, and originally it was a question about for testing magnetism, and the described experiment involved a loudspeaker made of cardboard. So it looked pretty much like what you see on the picture. So it had plate made of cardboard, and then a cylinder glued to it, and the coil wrapped over. And when the student brought a magnet next to the coil, it oscillated, producing an audible sound. So I came with this idea to Henrik: how can we do this in 3D printing? And my original idea was, let's make it out of cardboard, but it would be nice to have the cylinder for the coil actually 3D printed. It would be a bit easier. And I said, I can print you the whole thing. I can print you it as a single piece. The filament that you print from is elastic. It will oscillate very nicely. And this shows you that how beneficial it is to have someone who actually has a lot of experience with 3D printing, because just the process of 3D printing, designing model, running the printer, this is relatively simple, but knowing properties of the materials that you work with, that takes experience, and gathering that experience really takes time. So it worked really nicely. So that works. So here we have a video. Well, I hope you heard Beethoven's Fifth Symphony. It wasn't very loud, but it worked. And what I really loved about it, and that students could have played with those speakers, but when I played, they were just running basic signals, like a single frequency. And when I run actual music from my laptop on one of those speakers, it took them a few seconds to realize that it's the speaker producing the sound. Like, they were looking around, like, is this from a classroom, neighboring classroom? Because yes, they heard that the speaker can produce a sound, but it took them a while to realize, okay, but that means that this thing can actually play music. So I think huge success here. Another model that we worked on was a simple DC motor. It is one of the topics that we have to deliver, and our problem. I was looking from some offering. We wanted students to have an opportunity to play with those DC motors, to actually touch them, feel that there is a force acting on a rotor, to observe how the commutator works. And I looked for some off-shelf offerings of educational stores, and the problem is that usually the models that you can buy are, first of all, expensive, so it's hard to buy many of them for the whole class. And second thing, they are usually much more complicated than what we want to show. So I would spend half of my lesson discussing, okay, but why this thing in front of you looks differently than what you have in the textbook and what I have just explained you on the board. So we designed this motor not to be the most efficient one, but to be the simplest one that allows us to actually discuss the concept of motor force acting on a rotor, and not to discuss too many side topics, so to actually concentrate on the main message that we wanted to pass. This motor, as you can see on the pictures, not everything about it can be 3D printed. We used copper sheet for a commutator. We have also purchased permanent magnets. Some screws were needed, but the main structure was 3D printed. So let's see how it works. Then you can see that it's working until it gets stuck at some point. So we also run at some issues. First of all, it took several iterations to get the design right, so that it's is robust and works as expected. And also, for example, what we realized only after running the class, that the filament actually melts at around 200 degrees Celsius, and we're running high current to actually make the rotor spinning. And when the coil gets hot, the whole thing melted a bit. Right, so yeah, we'll have to fix our models now. But the good thing is, if it's broken, then we can just print another one. It's very, very easy. So we have no worries that someone will damage it. We can really just give those models for students to play with, and even damage them and learn something through it. And the third example, this is actually not our idea and not our model. We haven't designed it. This was designed by CERN. They have an initiative called School Lab, and one of the things that they offer is several activities based on 3D printing. And this model is used to demonstrate principle scattering experiments. So you launch a bunch of particles at a certain target. Those particles scatter in different directions, and then from the distribution of the scattered particles, you try to figure out something about the shape of the thing that those particles hit. So you can see that there is a ramp here, a blue one. On the first picture, you can see that there is a row of bearing balls on the ramp. You move the slider on the ramp, and the balls roll down, hit the target in the center. Here we have three circular targets visible, and I believe this is supposed to model 3 quarks present in, let's say, a proton. And the balls scatter in a certain pattern. And it really, really shows you the idea behind the scattering experiment. And even better, the models include a cover. You can put a cover on the target. You can give students an unknown target, and then they have to figure out. What is there? There are several targets, the one you see on the picture, but there's also a rectangular target, a simple cylinder, triangle, and they really produce different scattering distributions. And if you can make it as a simple activity just to get an idea, or if you have time, you can make it more complicated. You can run even proper statistical analysis of the results if you have time and opportunity. Now, the issues here, for example, with this model, is that it's large. It's large and it requires a lot of filament. So when you wanted 6 copies of that, it took I think over a week to print all of them. Just the base plate was about 6 hours to print. So those are sometimes the prints are time-consuming, and you have to plan in advance to get a sufficient number of parts. And lastly, something very simple and maybe less spectacular, but a magnet holder. This was really simple item. We were running the experiment. You can see on the bottom we are measuring magnetic force acting when a wire, current carrying wire, passes through magnetic field of those magnets, and to generate noise. Supposedly uniform magnetic field, we wanted to put them exactly in parallel, and yeah, we printed a simple holder. The holder is made so that you can slide in magnets, so you can easily replace them with a different kind. So we deliberately bought magnets. You can see in the picture, but so we have neodymium magnets of the same size, so you can experiment with different field strength, and yeah, that was really a huge success. The same model was later reused for a magnetic swing. You can see now that when you run current, the wire moves. Magnetic magic, and we used a lot of items like that. So clips, holders, stands. Whenever we want to improve a certain experiment, we can just add a simple part that makes the whole thing more robust and easier to use. And usually those are things that can potentially be achieved with cardboard and hot glue just as well. But it's simpler. Once you have one model, you can just start a print and collect it a few hours later. So you only have to invest that initial time, and then it's there waiting for you. If you need more, you print more, and it's not a problem. And just to finish with some other items that we used. So on the left you have a glider for our air track. Unfortunately, some of our gliders bent because they fell on the floor. They weren't working properly, so we printed ourselves another one, and it works just as well as the original metal ones. We also have on the upper right, we have a ramp that was used to investigate conservation of momentum in collisions. We wanted a way to repeatedly roll balls with similar speeds so that they hit other balls, and the ramp, like you can see on the picture, was used for that. And lastly, a projectile launcher. A very simple device. You just put a rubber band. It's not on the picture, but you put a rubber band and it acts as a catapult, and you can get very similar projectiles multiple times. Great for investing projectile motion. If you were to buy something like this, I think I even checked the price yesterday. It's about 500 euros if you want to buy professional projectile launcher. And this one, I know, the cost of filament didn't even register. So really 3D printing provides you with a lot of opportunities. And one last thing before I finish, because during this conference, there has been a lot of talk about projects in education. So nice thing about 3D printing is that a lot of those things easily scale. So if you just want a quick demonstration made by you, you print 1 copy. You want students to play with it, you print 6 or 10. You have a bit more time, you want the student to gather more experience. Instead of providing them with an assembled DC motor, you just give them parts. And they have to build it, wind up the coil, put everything together. And if you have really, really a lot of time, then why not ask students to design their own DC motors? There's a lot of many free programs to create 3D models, and students can do that on their own, and you can print their designs and well, discuss them. So that's it for me. I don't know if there are any questions. Thank you very much.
Thank you. Ja potwierdzam, że się...
I will just confirm that the filament melts. I was the one who did not read up on the 12-volt maximum margin. But, you know, even if it melts, you just print it out again. So this is genius. Another thing, if it ever happened to you to buy a lens, buying a lens that says for educational use, it costs 60 zlotys. If you buy a lens somewhere out in the market, it costs half of that. So it's better to sometimes just make things yourself.